Welcome to qnawire.
In this problem, we have to find the weight of a satellite in orbit around a planet. The first thing that we want to do to approach this is make sure that all of our givens are in terms of units that we can use. So for example, our period t is given in hours, but when we're doing physics, we always work in seconds. So this is equal to, we're going to multiply it by 60 twice in order to get a period of 7,200 seconds. Additionally, we're given both the radius of the satellite as well as the radius of the planet. But remember, the total distance between a satellite and the center of mass of the planet it's orbiting around is the radius of the satellite and the distance between the satellite and the surface of the planet, plus the distance between the surface of the planet and its center of mass. So we're going to rewrite our quantities in terms of the total radius, which is going to be just equal to the addition of our two radii, and that's going to be equal to 4.56 times 10 to the 6 meters. All right, so now we can begin actually thinking about the concept of our problem. So we want to find the true weight of the satellite. Now, we know that to find the weight for any object, we need to look at the total gravitational force acting on it, which, as we know, is equal to m1 times m2 times the gravitational constant over r squared, the distance between those two. Now, that means that g, the gravitational constant, is always proportional to 1 over r squared, since that distance is what determines the acceleration of gravity. That means that we can say that it is equal to some constant k all over r squared. And since we don't know the mass of our satellite, or since we don't know all the masses in this problem, that's going to allow us to solve. So for every satellite problem that we're given, we know that our centripetal force is equal to our gravitational force, since the attraction of gravity is what is causing our object to move in a circular orbit. So that means that mv squared over r is equal to mg, which in this case is equal, or that we are saying is equal to mk over r squared. All right, now from here, we can rewrite our centripetal force so that we have it in terms of t, our given quantity, since we're not given a velocity. We know that t is equal to 2 pi over omega, which we can rearrange. And since we know that omega is Vr, we can rewrite our quantity up here as m omega squared r and set that equal to mk over r squared. Simplifying in order to solve for k and getting rid of our m's, we get that k is equal to omega squared times r cubed. And plugging in what we just found from our period, we know that that's equal to 2 pi squared over t squared times r. Remember, that's our total r that we found earlier, cubed. Now, when we plug in our quantities here, we find that k is equal to 7.22 times 10 to the 13th. So in order to solve for our weight, all we have to do is plug in that equation that we found earlier, mk over r squared. Remember, we only have mass because we're calculating the weight. We only have one mass, we're calculating the weight, not the total force. We plug in all of our givens, 5,850 times 1, or 7.22 times 10 to the 13th, and divide that by our total radius, 4.15 times 10 to the 6. Remember, we're using the radius just of our satellite now, and square that. We get that the total weight, or true weight of our satellite, is 2.45 times 10 to the 4 newtons. And that is our final answer.